Okay, so let's give you a brief review for previous class. In previous class, we talked about the electron migration. That means the mass transport under the electrical field you apply on these materials. So we can simply divide it into two categories. The first one will be the ionic materials, and we are going to talk about the atomic flux of diffusing atom at interstitial, diffusing ions at interstitial site in ionic materials. And the second category will be, we will put more efforts on the metal materials. So you apply an electrical field on materials, and we are going to figure out what's the atomic flux of interstitial ions, metal ions, and all the metal ions at the substitutional sites in the pure material, in the pure metals. Then at the end of this sections, we are going to give you two case study to show why the importance, why the electron migration is so important. Okay, so in the first category, what we talk about will be the ionic materials. Then people will adopt some interstitial positive charge at the interstitial site, and the concentration will be the dilute concentration. And then we apply the electrical field on this kind of materials. So and we want to know the first thing is what's the atomic flux of this interstitial ions, and then what's this flux, what is the current density, what's the relationship of the current density and the atomic flux of this interstitial ions, what's the relationship between this. So in order to understand the driving force act or apply on these positive ions, so because you want to know the flux, right? So we need to formulate the potential of these positive ions. And if you take carefully on these examples, you will, how many possible driving force be applied on these ions will be two, right? The first one probably is due to what, the concentration gradient, which is the driving force will be the chemical potential gradient. And because you also apply the electric field on this system, so the second driving force here will be the electrical potential. But here we need to modify that because the driving force here, driving force will be the electrical field or minus electrical potential gradient times the charge it carry on this positive ion. So we besides the chemical potential, we need to add it the extra term, and it will be the Q1 times the phi. And then we can simply formulate the atomic flux will be due to the concentration gradient and the electrical field will apply on this system will be the mobility concentration and the driving force here. As long as we know the atomic flux of this interstitial, then we times the charge carry on these ions, then we can get the current density. And this current density, current density always obey the Ohm's law. So compare these two terms, you can get the electrical conductivity of these doped ion materials will be associated with diffusivity of this doped particle, these interstitial ions into this matrix, and also the concentration of this these positive ions and also the charge is carried on these ions. Okay, so this will be, but here just remind you, after apply an electrical field, there's a positive charge ion at the interstitial side is going to move toward to where? Toward to cathode, because this is positive. So after you apply an electrical field, it's going to move to the cathode side, right? And next, the second category would be you apply an electrical field on the metal. People call it this electron migration. And this effect is a cross effect between the diffusing species and what? And the electrons driven by the electrical field you apply on the system. So the reason this mass transport of these positive metal ions is due to the bombardment of the electrons and through the momentum exchange or momentum delivery. So why this is so important? Because as long as these metal ions be pushed away their lattice point, then it will left a vacancy here, and as long as then if you have lots of vacancy, and vacancy will grow to form a void. So if you take a look on this connecting line in the IC chip, you can find that there's some void into this connecting line. As long as this void get larger and larger and cover whole connecting line, then it will fail this IC chip, this device. So this is why the electron migration is so important. We want to avoid, be an IC designer, we want to avoid the EM damage, included the void and also the extrusion we mentioned in previous class. Okay, so in order to quantitatively calculate the atomic flux driven by the electrical field you apply on these metal materials, then you can formulate the interstitial atomic flux. This interstitial atomic flux directly driven by the electrical field and also the chemical potential gradient. And for this term, we also can rewrote it as a mobility, concentration, and driving force. The driving force here is not equals to electrical field you apply on the system, because the reason to this interstitial atoms moves is due to the bombardment of the electrons. So you need to write down as the driving force here will be the beta E, and beta is effective charge. And this effective charge is a summation or summary of two forces, electrical forces presented in presenting or acting on these atoms. It included what? The field here is the static electrical field. This is a positive if it is a positive interstitial ion, like it's a metal ion, positive, right? So when you apply an electrical field, this positive metal ions is going to be pushed toward to cathode. But the electron flow is going to push these atoms toward to, or ions toward to where? Anode. So the effective charge is a summation of this effect, including the static electrical field and also the electron wind or electron flow. Okay, so after series, and just substitute this term here, then you got the interstitial atomic flux can be expressed like this. And if we assume it's a dilute doped, I mean the concentration of these interstitial atoms is quite small. and there's no gradient on it, so you can just simplify the atomic flux expressed like this term. And then this slide is going to demonstrate that how we measure the beta, this effective charge. In the beginning, you have your materials with dilute doped interstitial atoms in the metals. Then you apply the electrical field with the direction to a left-handed side on it. And as long as the concentration profile of these interstitial atoms do not change over time at this moment, that implying that the two flux equals to the value or magnitude of these two flux are the same. That means the net flux is equals to 0 as long as as long as the materials reach this quincy steady state, then you can calculate the beta by what? But you can use the EPMA to get the concentration gradient of these interstitial atoms along your materials, and this is the electrical field you apply on this system, so you know that. And you also can know the concentration of these interstitial atoms, and this is a working temperature, so you can easily get the effective charge of these materials. And as we mentioned, the beta, the sign of the beta just tell you the direction, the moving direction of the diffusing atoms, right? So in this case, in metals, usually the electrons is going to, properly here. Okay, so here in metals, usually the effective charge will be negative because due to the bombardment of electrons, so this diffusing atom is going to be pushed toward to the anode side. And the negative means the same direction with the electrons flow. In some special cases, if the beta is positive, usually means the diffusing atom of vacancy is toward to in the same direction of the current flow. Okay, so the sign of the beta tell you the moving direction of your diffusing species. Okay, and we also talk about in previous slide. Actually, we talk about interstitial atom in metal, right? That is the atoms at the interstitial side. But here we talk about the atoms at the substitutional side, and which is in metal, pure metals. So it's very difficult because there's only two components in the systems: it's atom and vacancy. So it's very difficult to us to plot the diffusion profile of the atoms. So in order to know the atomic flux of these atoms at the substitutional side, we will use we can much easier to track the vacancy. So we get the JV, the flux of vacancy, then we can get the JA. So it will be the mobility of vacancy, concentration of vacancy, and driving force acting on this vacancy. So it's easy. We can use some material analysis tool to know the concentration of vacancy. For example, like STM or TM. And mobility of vacancy, yes, is much easier because it's a vacancy, so it's easier to measure that. And the driving force here will be the beta E. And the beta here is a beta V. We label V is the effective charge of vacancy. The difference between the beta V and the beta we mentioned in previous slide is a sign. Vacancy it always is some people will consider it as a positive upside charge of the metal ions, right? So if the metal ion, for previous case, the metal ion is moved toward to the anode, it can tell you that the vacancy will be go to the upside direction, right? Will be moved to the cathode. So the sign will be different, but the value will be the same. So here, beta V is the same value with beta, but it's a different sign. Because different sign means the moving directions, right? So if your atoms move to the anode, then implying that the vacancies will be moved to the cathode, right? Okay, so that's why we label that, it's beta usually is positive here. Okay, so we finished the electron migration part. Then we are going to give you two examples, two case studies to explain why the electron migration is so important. The first majority effect, we call it a Blatch effect or backstress effect, and the current cloud will be the secondary effect. Let's move to the Blatch effect first. What's the Blatch effect? Some people call it a short strip effect. That means that if you take a look on the definition, here will be the no electron migration damage when the strip length is below a critical value. What this means? Let's take this as an example here. The bottom part is an oxide, silicon oxide substrate. On the top of it is a molybdenum line, and on the molybdenum line, there's an alumina line with higher conductivity. So when you apply an electrical field on it, you can observe there's a current, electrical current goes to the left-handed side, and that implying that the electrons will go to the right-handed side. And because the alumina has a higher conductivity, so electrons flow will go like this way and go up and go to the alumina line. Then these electrons have chance to push the alumina ion toward to right-handed side, which we call the electron migration. And as you know, the net flux will be equals to 0. So as long as the alumina, the atomic flux of alumina be pushed to right-handed side, that implying that there's a vacancy flux toward to left-handed side. If the JA and JV is quite large, it's possible to have the extrusion on, you can observe the extrusion on your right-handed side, and because JV is large, then you can observe a large void form at your left-handed side, or you call it is at the cathode, right? So if after longer time, what do you think? Probably you expected the extrusion would get worse and worse, and you can observe the void get larger and larger. But however, scientists observe one very interesting thing is if this line, alumina line, get a smaller or shorter with a shorter length, this is people is not going to observe the extrusion and also the void during these settings. That implying that what? Material has some internal force to counterbalance this atomic flux driven by the electrical field or driven by this electrons flow. There's the other driving force to counterbalance this effect. So what kind of intrinsic material property we are talking about? So there's an internal driving force. Actually is what is the is we call it is a stress field of these materials due to this JA atomic flux. Lots of more atoms will accumulate on the right-handed side, and the result the vacancy presented at the corner at the cathode or left-handed side. So based on these figures, you can find there's more atoms here, right? So it turns out something like compressive stress. And this is some vacancy. More vacancy exists here, so can consider tensile stress. So there's internal stress field exists in these materials. So this stress field will serving a driving force to counterbalance the atomic flux driven by the electron migration or driven by the electrons flow. So this is the other driving force to counterbalance this effect, right? So in these materials, so in this alumina line, there are two driving forces. As long as the magnitude are the same, then what? You are not going to observe the extrusion and void. In the other words, would be if the atomic flux driven by the electrical field is smaller, the effect is smaller than this stress field induced atomic flux, then you are not going to observe the EM damages. So that critical length we call is the critical value here. So how to determine this critical value? So in your textbook, they give you these examples. We want to know what's the critical length for the connecting line or for your materials delta X. So yes, you can. In this case, we draw the direction of the electrons flow. So electron is going to up and down, and you can observe. In the number one, case one, you didn't observe the extrusion and the void formation. But as long as this length gets longer, then you can observe the EM damages, including the extrusion and the void formation. So in order to know the critical length, LC here, so you need to write down what all the possible atomic flux exist in this line. Or you can call it like probably you can think about how many driving force apply on these materials. As long as they can compensate, then this effect is not going to happen. I mean, the EM damage is not going to happen. So in order to that, here we use the JA, is atomic flux of atom A. And because there's an electron flow goes through this material, so possible will be cause atomic flux driven by the electrical field. We call it the electron migration, right? So can be the effect will be here. Due to the electron migration will be the mobility, concentration, and the driving force will be beta E. And due to this EM effect, this EM is going to push more atoms accumulate on the right-handed side, and more vacancy presented at the left-handed side, and cause a stress field within it, right? So this stress field will also driven the mass transport. So the effect of stress field here, we just we can write it down here, and we can express as what? Mobility, concentration, and the driving force. So what's the driving force for the stress field? Any questions or any idea for this? It will be a driving force. So in the beginning, probably you will think about the driving force, the force. So if you need to think about what kind of work apply on this stress. I mean the work related to the stress field. Because usually people do the work divided by length, then can be considered a force, right? Stress force. So the upper portion will be the work, and the bottom is divided by the length. Then you got the force, right? So the work here would be what? Would be the stress, right? Stress, the unit for stress is the force, the applied force per how much force apply on the unit area. We call it is a stress. So stress times the volume, you got the work, right? Because you drop this turn and you get the length here. So force times the length, you got the work. So the stress times the volume, you will get the work. So here will be the stress, so will be the gradient, so will be the stress, and times the volume will be the atomic volume omega. So based on the unit part, this term would be the force term, and this is also the sigma dx is the stress field we just mentioned about, right? Because the EM, there's a stress field applied on this material, so this is a stress gradient. Yes, it's stress gradient. In your textbook, it calls it a back stress, a gradient of back stress. Okay, so here, yes, you can just directly formulate this term. And in quasi steady state, that means these two flux, if JA equals to 0, that means the atomic flux driven by the electron migration will be equals to the atomic flux driven by the stress field. At this moment, then these two terms are the same, so you can get this equation, right? And just after arrangement, you can put the JE and the delta X together, and the rest of part to the other side. Then you can get this critical product. Is the current density times the delta X is the critical length of this metal or these materials, equals to what? Equals to the stress gradient or stress difference times the atomic volume, electrical conductivity divided by effective charge. What kind of materials property? What material property is suitable to be used to represent or present this delta sigma? Then in order to determine what kind of material property, probably you need to think about the sigma is the stress, right? So are there any material property is related to the maximum stress this material can afford, right? Because as long as the stress is get larger and larger, then you can observe the deformation of a material. But below this stress, you can observe there's no deformation of this material. So are there any material property can associate with this delta sigma? I believe some of you already have this kind of idea, right? Related to previous background on the material science. This is the stress, the figure of the stress versus the strain. And this is the stress-strain behavior of metals. And this is a linear region. That means when this material suffer or subjected to this stress, and it will cause this kind of strain. But as long as you remove this stress, then this material will go back to its original diameters. There's no any deformation found on these materials. But as long as this is linear region, right? So as long as when you increase the applied stress, and there will the strain, the corresponding strain will increase in the meantime. So you can observe this linear region. We call it as what? Elastic behavior of these metals. As long as within this region, as long as you remove the stress you apply on these metals, you remove it, then these materials go back to its original diameters. There's no any deformation. This will not cause any deformation of this material. But however, if you increase the stress above this, we call it yield stress, then as long as the stress is larger or higher than this yield stress, then you will cause what? The deformation of these materials. And this region, we call it is a plastic region of this material. You will call the deformation. So this is, so you can, yield stress can be considered as a maximum stress this material can be subjected, and that won't cause any deformation of this metal. As long as the stress is higher and then this yield stress, you definitely will cause some deformation. For example, it's like this, right? The extrusion or the void form. This is a typical deformation of this material. So this delta sigma, you can use the yield stress of this material to represent this. So you can have an idea about the right-hand side, this region. I mean, this is related to material properties. So as long as you decided what kind of materials you are going to use as a connecting line here, then you can measure the conductivity, atomic volume, and also the yield stress, and also the effective charge of these materials. And your left-handed side will be more related to the IC design, right? As long as you know what kind of chip or transistors you are dealing with, then you can determine the current, the necessary current density for operate this device. And then you can know, this one and the current, then density, then you know the delta X. So you are going to get the maximum length of this connecting line you can design to avoid the EM damage, including the void formation and the extrusion. So this is we call a critical product, the current density times the delta X. Okay. And this is a major effect we call a Blash effect caused by the electron migration. But there's also a secondary effect we call it a current crowding effect happen when you apply an electrical field on these metals. So let's take a look on the figures we put here. Is now we have a titanium nitride, and on the top of titanium nitride there's an alumina line, connecting line here. And as we mentioned before, we will apply an electrical field. So you can observe what? You can observe current passing through this alumina line, and due to the electrical conductivity of alumina is higher than nitride, titanium nitride, so the current usually will the direction will be like a passing through here, then go up, goes through the alumina line, then go down and go to a left-handed side, and this is the direction of current. So if we want to plot the direction of the electrons, will be the upside direction. Will go here, right, and go up, and passing through this alumina line, and go down. So in this case, you can observe what? You can observe this dashed line is the directions, the distribution of electrons flow. Then you can observe this is the what? Usually, as long as this electrons flow is high enough, then based on electron migration, you can observe the stress field, because the alumina atom is going to push to the right-handed side at the cathode side, and the vacancy form at the anode cathode. This is will be more atom be presented at the anode side, and there are some vacancy accumulate at the cathode side, right? And based on this geometry, you can know this will be inhomogeneous stress, or you can call that inhomogeneous current or electric current distribution, right? Because there's more higher current density within this region, but there will be low current density at this corner region. So if you try to run the simulation of the current density on the alumina line, then you can have this results. Take a look here. The light gray one is showing the low current density region or high current density region, and the darker gray will present is the lower current density region. So you have take a look on these results. You can observe that this region, light gray region, is belongs to high current density, and as we expected, at the corner side there's a low current density region, low Je current density region. And if the current density increase and cause the EM damage, including the extrusion and the void form, probably we can show this. We are going to observe this phenomena happen on this alumina, right? But besides this electron migration effect, we also some scientists also observe the secondary effect. Is they observe there's also some void form in the low current density region, like this region, this corner. This is a low current density region. So some scientists will ask why. So if you, in order to investigate why, probably you can consider this vacancy here. The vacancy now is located in the middle of the electrons flow. So majority or almost most vacancies will be pushed by the electrons flow, but some vacancy will be pushed toward to the region with low current density. Why? You can think about that. V equals to IR, right? So if I ask you about the potential of this vacancy, IR, the resistance almost the same, so we can put more effort on the current I. If the vacancy located here suffer the higher current density, right? So means higher current density means you have the vacancy will have a higher potential energy. And here, if a vacancy will locate here, and the current density is lower, right? So it will have a lower potential. So there's a potential gradient along these directions due to the inhomogeneous of the current density. This is higher current density and this is lower current density. So in order to decrease its own potential energy, some vacancy is going to move toward to the region with low current density region in order to decrease the total energy or total potential energy of the vacancy. So people is going to observe some void form at the region with low current density. Actually, this in previous slide, we also observed this phenomena. Here, for example, here we point out the direction of electrons flow, and you observe some void form along this the path of the electrons flow, right? But interesting thing happen here. This region actually definitely is a region with low current density, right? Because the majority electrons go through here, right? Not here. So this region definitely is a low current density region, but we also observe the void form here. This is the evidence of the secondary effect we call the Kerr cloud effect, what we just mentioned. So this is the evidence demonstrate that the exist of this secondary effect or current cloud effect happen in our connecting line. So, okay, so let's move back. So majority effect is a Blatch effect, or we call extrusion or void form. This is EM damage, and besides the EM damage, the extrusion and the void form at the high current density region, at some low current density region, we also can find some void form at that region. Okay, so we are going to use this example to end these sections. So this is what we have here. Is we consider a alumina line. This is the alumina line, and the diameter of this alumina is 0.5 micrometer, and the length will be 5 micrometer. And the effective diffusivity is 10 to 15 centimeters square per second at 115 degrees C. The effective diffusivity means we measure the diffusivity on this alumina line, that we got this effective diffusivity. Or some people call it apparent diffusivity. Okay, so the question here would be, please answer or estimate the time required for forming a void. And the void size will be 0.5 times 0.5, so cubic micrometer, at the cathode side of the alumina line, subjected to electrical current 2 milliamp at 115 degrees C. Then the following is the related information provided by these questions. So you need to draw these figures, and this is 5 micrometer, 0.5 and 0.5, right? And you apply electrical current, so current is go to left-handed side, and it's 2 milliamps, so the electrons will be go to the right-handed side, and you there's a void form at the cathode, so there will be a void form here, and the size will be here. So please estimate the time required. So in order to get the time, so we know the void size, right? The size of the void. So probably you need to know the vacancy flux, because vacancy flux is the reason to form this void. So the vacancy flux, the unit for vacancy flux will be, this is a pure metal line, right? So the vacancy flux can be considered the JEM. And JA, atomic flux, will be equals to J vacancy, right? So based on this concept, we vacancy flux will be can be expressed like the number of atom or number of vacancy formed per second per area. And in order to know this is a flux, right? So we times the area, and also the volume, atomic volume. So you are going to know what the total volume or the total volume of vacancy form per second. So based on this, we use the void total volume of a void divided by this term, then we can get how much time we need to form this void. So the vacancy flux will be the key point here. And this area is this area, right? And omega is atomic volume here. So these two parameters we know. So the key point here will be the J, atomic flux or vacancy, or atomic flux caused by the electron electrons field or the vacancy flux. Either way, because they are the same value, just an upside sign of JV and JA, right? Okay, so this is what we need to know. So how to get this value for the flux, atomic flux or the vacancy flux? Mobility, concentration, and the driving force. So mobility would be diffusivity over kT. Concentration would be the concentration of alumina. So this JEM is atomic flux of alumina. And the driving force is beta E, right? So regarding to the concentration of alumina, actually this is looks like it's a pure metal, right? So how to get this? There's a relationship you learn when you derive the Einstein relationship, right? It's atomic fraction of alumina equals to atomic volume times the concentration. So this is a pure alumina. So atomic fraction here is 1 over the atomic volume, and you got the concentration of alumina. So it's expressed here. In order to make sure the unit will be correct, so I always put the unit here. So the unit for concentration will be a number per cubic centimeter here. And the diffusivity, the questions tell you is 10 to minus 15, and put the unit here. And the bottom will be KB. KB will just copy here. And the E here, I put here EV divided by K. And the T here, I converted to the K will be 423K. I put a K here. And the beta will be what? The beta will be minus 10E. Beta, I put a 10 here and the E here. And the J current density here, the questions only provided the current, so you need to divide it by the area, then you can get the current density. And I put a unit here. And also the low is the electrical conductivity, and put here and unit here. Then I check the unit before I use the calculator to count this value. Check the unit. I drop this term, 2 turns out, and K and EV, because E here and E is the charge carry. The E is the charge, right? Carry on the electrons. Okay, so drop this term out, and V equals IR. So let's drop this term. So what we have is the flux, the unit should be cm squared per second. Number, how many alumina atoms passing through this centimeter square area per second, right? So it's perfect. So this is the JEM. Then I just use this term to substitute this term, so I can easily get the time will be like this, will be like 2.8 years, around 2.8 years. So this is how we deal with this kind of questions. So afterward, if the question asks you a time period, this is a time. So first thing you come to your mind will be you need to know the flux, because flux is per second, right? The unit will be how many atoms passing through unit area per second. So you know how much time it takes for forming a volume of what, something like that. Okay, so so some people ask about the beta. Beta for metal usually, as we mentioned in previous slide, will be negative. So here negative 10, E here probably is 1.6 10 to minus 16 or 19 is a charge it carry on the electrons. Okay, so here we didn't put the minus here. The reason for that is in order to calculate the time required for forming a void, the direction of the electron, the direction of the atomic flux is not that important here, so we didn't put the minus here. But based on this figure, you know the J atomic flux of alumina will be toward to anode, right? Or toward to right-handed side, because it be pushed by the electrons flow. Okay, so let's give you a quick summary for of the electron migration. Electron migration, we talk about is a cross effect between the diffusing species and the electrons flux, and through the momentum exchange effect. And that's a very important parameter, beta. We call it the effective charge to describe the direction of this atoms moving species. If the beta is negative, that tell you that the direction of moving species is the same direction with the electrons flow. On the other hand, if the beta is positive, that the moving species probably is vacancy or something, is toward to the same direction with current. Okay, and in metals, can be divided into two different conditions. The first one is we talk the atomic flux of interstitial atom, and the second one would be the substitutional atom. And you can easily write down for the interstitial one is the concentration gradient part and the electrical field part, and the substitutional part, due to it's a pure metal, so the only way you can know the atomic flux will be by calculate the JV, vacancy flux. So it will be the mobility, concentration, and driving force. And also the EM flux is counterbalanced by the flux driven by concentration gradient or stress gradient. Stress gradient part will be the latch effect we just talked about, right? So are there any driving force can counterbalance the atomic flux driven by the EM or driven by the electrical field? Yes. The first one is the concentration gradient, right? And the second one is a stress gradient. Okay, so give you a summary for the EM. The driving force for EM here we usually we derive here will be the minus beta effective charge times the minus electrical potential gradient. Based on this, you can formulate atomic will be diffusivity, concentration, driving force. We want to list this due to in the end of lecture 1, when we talk about the driving force for electrical field. At that moment, the driving force we tell you is the minus electrical potential gradient. But if the case we are talking about is electron migration, that means this migration is due to the electrons flow. This kind of situation, then you need to replace or you need to modify the driving force by ending the beta here. So it will be the minus beta electrical potential gradient. Then because the driving force be modified, so you also modify the atomic flux here. Okay, so next we are going to talk about the thermal migration.